Welcome to Constellations, the podcast from Kratos, where industry leaders share their thoughts and experience on the future of space business, policy, and opportunity. If you like Constellations, please support us by giving a rating and review on iTunes. And don't forget to share this podcast online to help our community grow.
Welcome to Constellations, the podcast from Kratos. My name is John Gilroy, and I'll be your moderator. Today, we are at the SmallSats show in Logan, Utah. During today's podcast, we will discuss the basics, and just the basics, of quantum information processing, how quantum key distribution, QKD, ups the game in data transmission security, and moving from the BB-84 scheme to fully entangled sources for small satellites. Wow. To help us maybe try to understand this complex topic, we have invited Dr. Mark Adams. He's an associate professor of electrical and computer engineering in Auburn University's Samuel Ginn College of Engineering, and also assistant director of the Alabama Micro Nano Science and Technology Center, where he established the STORM Lab. Nope, not Oklahoman tornadoes. This is a different storm. This is an acronym that stands for Sensors, Transducers, Optics, RF, and MEMS. The STORM team focuses on progressing the technology of quantum key distribution. Boy, you sound like you're a Spock or something, with all this background. That's incredible.
Well, thanks for hosting me today, John. I certainly appreciate it. We do a lot of fun things in the lab.
Yeah, I guess. Yeah, you get your reputation out there, and all the smart kids want to apply and work with old Mark, huh? Excuse me, Dr. Adams.
Well, yeah. They have to call me Dr. Adams. You're fine calling me Mark.
Well, here's the easy question. It's probably take you 30 hours to answer this, but you got try to give us like a normal human being answer. So what is quantum information processing?
So let's start with classical information processing to kind of set a baseline. So everything you do today pretty much revolves around some type of information and taking that information and making reasonable decisions with it. Classical computing, for instance, the things you use on your PC, your laptop, your phone, those all just harness the properties of classical electronics and classical communications in order to make that happen. So what's the difference between quantum and classical? Well, when we start introducing quantum, we start to access properties that are unavailable in the classical realm. And so by taking these inaccessible properties and leveraging them for quantum systems, we're able to do some pretty unique things that you can't do on a, kind of standard classical technologies.
Yeah, I'm reading this morning, and you try to take and harness some rules of nature or some natural processes. Is that right?
That's correct. And so back at the turn of the 20th century in the 1900s, right, when quantum mechanics was really coming into existence, the theorists postulated that there was all these interesting properties that we could take advantage of if we could just figure out a way to harness them. And so these natural properties are things that now we as engineers have learned to harness and apply to more traditional processing. So the QKD, for instance, we're going to talk about today, is just a quantum way of doing encryption. So it's all interesting.
You think about the turn 1900, there were so many smart physicists that all just popped out. It's like it was springtime for physics, wasn't it?
It was incredible, right? I mean, you just look at the number of just phenomenal, intellects that existed, from really the end of the 1800s to, kind of the early 1900s, 1920s, 1930s. Of course, everyone knows Einstein, but there were so many more, in that period of time.
I'm sure your students have read Thomas Kuhn's book, Structure of Scientific Revolution. He talks about just, like two people invented the phone at the same time. And so we know breakthroughs were made around 1900 in many areas, and one was quantum. And so this isn't the new kid in the block. This has been around a while.
Absolutely.
Maybe for our listeners, give us some examples of how quantum information technology has been applied in the past.
Sure. I think one of the things that people need to realize is that you interact with quantum systems on a daily basis. You probably just don't really realize it. And so lighting, for instance, is one that comes to mind. Fluorescent lights, fluorescence is a quantum phenomenon. And so if you didn't understand how that worked, you wouldn't be able to take advantage of the light bulbs that are in the ceiling right now. LEDs, once again, quantum phenomenon.
Really?
Lasers. Most of the microelectronics technology we leverage today really stems from quantum mechanics. And so there's just tremendous examples throughout the past of how we've leveraged that to really progress society from a technological standpoint.
Who knew, huh?
Yeah, I think people just overlook it. And there's a good reason why. Don't get me wrong, right? Not everyone needs to understand the fine details of how all of that works.
Yeah.
They just need to be able to leverage it, right, to take advantage of it.
So we have the concept of quantum mechanics, and the whole idea of quantum is fine. And we're going to talk about applying it to one area of science, one area of mathematics, whatever you want to call it. And this is quantum key distribution, or QKD. Now, I'm so old, my math teacher used to put QED at the end of the chalkboard there, chalk chalkboard.
Chalkboards.
So, but QKD.
QKD.
So, quantum key distribution. So we set the stage for quantum. Now we're going to up it up to key distribution, right?
Correct. So we're going to take advantage of some of these properties to improve the security of communications. So let me set the stage just a little bit in terms of why it's important. So most people are probably at least heard of quantum computing and the fact that quantum computing is coming online maybe in the next 5 to 10 years, depending on who you talk to. Existing security relies on algorithmic type encryption techniques, which means we have a really hard equation we want to solve, right, in order to encrypt data. That works perfectly fine with modern-day computing. It's hard to crack it. It's hard to actually hack that quantum or that encryption. The problem is quantum computing, because of it takes advantage of these quantum properties, can do it very quickly. So as soon as those quantum computers come online, traditional encryption techniques are kind of go to the wayside. Pretty much all civilization knows that at this point. And so most government entities are interested in finding ways to do what's known as post-quantum. Yeah. So one of these is to actually take advantage of the quantum properties themselves to make it resilient against these type of quantum intercepts that can be done. So QKD is just that. We're taking advantage of the quantum properties in order to create a secure communications technique that a quantum computer can't really hack.
Another old-fashioned analogy is, so they see the train coming and quantum's going to be a big impact, so they're thinking of alternatives to trying to maybe stop some of the impact of...
That's correct, to get ahead of it.
Like breaking your cryptography today.
Absolutely.
Yeah.
And so everyone relies on cryptography.
Yeah.
When you pay your bills online, right?
Right.
You're expecting that data to be secure.
Those Israeli guys, RSA guys, we're kind of relying on them, and that's kind of the standard now. And so they're actually human beings doing something preventative. I mean,
yes, I know.
True?
I know. It's crazy.
It's a breakthrough.
Like, yeah.
So I go down to the old Best Buy and I walk out with a little computer and I start doing this technology on a standard garden variety computer. So what kind of infrastructure is needed to support this QED in a satellite or on the ground?
Yeah, so it's a little bit more technologically advanced than you can buy at Best Buy.
Oh, come on.
I wish it wasn't. I really do. I would love to be able to just go buy it off the shelf. So what we're doing currently with our scheme is relying on quantum optics. And so we're using optical generation of photons, right, which is the quanta of light, in order to do this quantum key distribution. And we're using a protocol called BB84, which was established by Broussard and Bennett in 1984. That's where the 84 comes from. So once again, been around a while, right? I mean, this isn't a new thing. But putting it into a small satellite is a fairly new thing. And so a lot of what we're working on is taking the technologies that have been developed and demonstrated in labs over the past 30 years in reducing the size, weight, and power, the kind of the swap, as we like to call it, in order to put it into the size of a boot box. And so there's a lot of engineering that has to go into that. From a technological perspective, though, what we're doing is we're using the properties of light in their quantum nature in order to secure the communications by sending a secure key. And so we can go into the details of that in a little bit, but that's what we're trying to do right now with our satellite.
I'm sure Auburn has computer science majors, and I'm sure they're forced to take courses in PKI, understand public key encryption, and go back and forth with the whole history of that. And so what you're saying is that this is just a different way to improve that encryption. So if I take out my iPhone, I'm pretty secure. But this makes, obviously, if it's a military application, this has to be the best encryption possible, doesn't it?
That's correct. And so one thing that all these techniques allow, so when we talk about QKD, they allow you to detect eavesdroppers. And so you can tell when someone's listening in on your conversation. And so that's a big deal, right? And so you can imagine if we want to spy on someone else, we don't want them to know we're spying on them.
Yeah.
So these techniques allow us to know precisely that someone has monitored that distribution.
Well, here we are at Utah State. Let's go over and grab a computer science major. And, Cybersecurity 101 is the man-in-the-middle attack.
Absolutely.
I mean, this has been around since forever. The man in the middle.
Absolutely the man in the middle.
And so normally this describes Bob and Alice and Eve. This is eavesdropping, the man in the middle, the person in the middle, but the man in the middle attack. And so there are ways that are designed with traditional systems to prevent man in the middle, and we can learn. They're in textbook now. They're literally in textbooks now. But there's no textbook for some of this stuff. It's really kind of new, and applying it is brand new, isn't it?
Yeah, it is. It's it's a relatively new field. I will say this: it's a little bit more developed for terrestrial applications. Uh-huh. And so, for instance, there's a number of companies now that are introducing quantum key distribution for optical networks, but those are fiber networks. And so, you've got to have Alice and Bob joined by a fiber optic. That's not really practical for everything, right?
Yeah.
I mean, you guys focus on communication from space. How do you do this from space? Well, that's what we want to do, right? We want to show that we can do the same thing you can do through a traditional fiber optic cable and do it from a low Earth orbit satellite to a ground station on space.
And if your students go to YouTube and type in QKD, they're going to get a whole lot of applications on fiber and talk about this many meters and that many meters. And you go, no, wait, what about thousands of meters? Well, we can't have a cable going all up to
That's
LEL,
exactly right. No, we can't. And so, we want to be able to make this more accessible, right? Yeah. So the best way to do that is put it in space, right? If we have an operational system in space, then it's accessible anywhere on the planet.
I love the royal we, especially at universities. And so your team, we are building a special proprietary open source QED system. Is that what's going on?
It is, yeah. So we're actually here presenting it at SmallSat. And so this is a project that's been funded through the University Nanosatellite program, which is sponsored by the Air Force Research Lab. And so we're doing this technology demonstrator, which will allow us to show that the key components of QKD can be accomplished from a small sat. It's tough. It's tough. Now, a lot of this has been demonstrated in the past with larger satellites. You may be familiar with the Mischief satellite, which was put up by the Chinese in 2016. It's a 600-kilogram satellite, so a large satellite, that was able to do this kind of QKD that we're trying to do with a 12U CubeSat. So, something, like I said, the size of a boot box. So it's a lot of a challenge there.
You used the magic phrase AFRL. My ears perked up, and I thought, brainiacs. That's the first word that came into my mind, And I've talked to those folks over there. And they study everything. For example, with the aircraft, they study, we have a plane on a desert 140 degrees. It's got to go up 20,000 feet, then go back down. And so they look at extreme conditions, don't they?
They do.
So they have to test wire endurance for extreme conditions. They have to. I would imagine that in your endeavor, you have to test for extreme conditions as well.
We absolutely do.
So that's part of the... you have to do the satellite, and what are the weather conditions in a satellite? Cold? Yeah.
Absolutely. So we do a ton of testing. And so at Auburn, we have the capabilities to do all the environmental testing that's necessary for small satellites. So we can test what the satellite would see on orbit. We can obviously test different types of environmental conditions. We can test vacuum. We also can test magnetic fields, so we can pretty much simulate what the orbit would look like for the small satellite. Now, the one great thing about small sats is they have short missions, right? We're not expecting them to stay up for 25 years. No. We're expecting them to stay up for 6 months to a year. So we don't have to have the resiliency that you would have in a large-scale commercial satellite. But it still has to work. I kid my students all the time. It's like we're not going to launch a space brick, right? We need the satellite to work, so we have to fully test it and characterize it on Earth.
Mark, thousands of people from all over the world have listened to this podcast. If you're listening now, go to constellationspodcast.com and get to our show notes page. Here, you can get transcripts for all 100-plus interviews. Also, you can sign up for free email notifications for future episodes. Well, Dr. Adams' humble John Gilroy is going to give you some advice. Recruit some physics majors, because my experience with physics majors is we have to build a machine to test, and they'll build the machine right in front of you and to test it. And that's not going to be an obstacle at all for a physics major. They're just going to plow right through it.
John, we have a number of physics majors on the team.
Good for you. Yeah, yes. We're putting a good team together then.
So, we have a very large team. Through our student program, we have the Auburn University Small Satellite Program. It's student-led. It combines teams from physics, engineering, pretty much any type of STEM field.
Yeah,
we have a representative from. So it's a
Auburn,
really great program.
At Auburn, we say you can't have all quarterbacks on your team, can you?
Can we get one?
One. That's good. Yeah. Well, let's talk about a different team, the Chinese team.
Yes.
I think maybe a couple years ago, 2020, there was some researchers. Maybe I saw a press release or something about they released their QKD technology. So big deal, speed bump, or.
Well, so one thing that the Chinese government has done is put a tremendous amount of money, significant investment into quantum. It caught the U.S. off guard, I think, a little bit. And so, we're starting to really ramp up our investment in quantum technologies. We had been relying on the commercial industries to really push quantum computing. But the other types of quantum communications, quantum sensing, those kind of things, we were kind of caught, I think, on a back foot by the Chinese when they put this up. And so they definitely showed that they were a little bit further ahead in some of the spaceborne technologies for quantum communication.
So the question is, how does your approach differ from theirs?
So one of the things that we're doing is, as I mentioned, we're trying to shrink it. And so they have a single testbed satellite, around 600 kilograms, at it's a fairly high altitude satellite, and so we would like to be able to do this across a constellation of satellites in low Earth orbit to produce global coverage, right? They have a single system up in space right now.
Degree of difficulty.
Much higher, yeah. However, the technologies are similar, right? So the fact of the matter is, all of these techniques were developed, as I mentioned, in the 80s or in the early 90s. And so from a quantum optics standpoint, we've known from a laboratory how to do this for quite some time. It's a lot harder moving it from a laboratory to a spacecraft, moving it from a spacecraft to a SmallSat, right? So to me, it's the next generation of what they've done to do it in a much smaller spacecraft.
Well, I talked about the physics majors. I'm going to talk about the English majors at Auburn. Now, they've all read George Orwell, and he wrote a book about 1984, didn't he?
He did.
He thought it was an apocryphal year. Well, guess what? It was.
No,
because of
to some degree.
BB-84, right?
Yeah.
In your world, it's got to be. So I did read this article, and it talked something about BB-84, and someone, maybe you, made a prediction that, probably by 2024, we'll be able to launch this project. So good prediction, bad prediction, or?
We definitely hope so. By maybe late 24, early 25. As you guys know, COVID has kind of done a number on everyone. And so, we have experienced some delays, due to the pandemic. But we're making very good progress. So I do think that we're on track to see like a late 24, early 25 launch.
So our friend George Orwell tried to predict the future. So I'm going to have you do the same thing, buddy. You're probably as smart as he is, understanding quantum. So what exciting developments, plans do you see in the next few years for you and your team, or maybe just as transition away from BB-84?
So for starters, we really want to get away from optical communications for the keys. So as you guys probably know, for optical comms, satellite-to-satellite optical comms works really well. You don't have the atmosphere to attenuate it. You don't have clouds. You don't have dust. But as soon as you start to try to get a key from space to the ground, all those artifacts start to impact you, right? It doesn't work real well if it's raining. It doesn't work real well if you're in a dust storm. You need secure, reliable communications. So the next step for QKD is to transition away from optical photons to microwave photons. And so we want to do microwave comms. You guys understand microwave comms, right?
Yeah.
So we want to be able to do the exact same thing we do currently using microwave technologies for high-speed communications, except for apply them to the QKD problem. So we've got efforts ongoing right now to do that. So we're really interested in developing entangled microwave sources to do quantum key distribution.
Well, I think this interview is going to get you a lot of applications to join your program. I mean, covered all the bases here. It's been really an interesting interview. Now, I think what you've done here is you've helped our listeners untangle some quantum concepts.
I hope so.
That's the word in your world, untangled,
yes.
Huh? Okay. I'd like to thank our guest, Mark Adams, Auburn University Associate Professor, Electrical and Computer Engineering, as well as Assistant Director, Alabama Micro Nano Science and Technology Center. Thank you, Mark.
Well, thanks so much, John. Thanks for having me.
Thanks for listening to Constellations, the podcast from Kratos. If you like this interview, please subscribe, tell a friend, and give us a review.